So this next problem is kind of like the granddaddy of all uniform circular motion problems. It's probably the most infamous one for lower level physics. It is what's known as the roller coaster problem. The roller coaster is this problem. So imagine that you have been hired to construct a roller coaster. You are designing the whole process all by yourself. You are going to start off with the first hill, which is the the uh, the highest hill in any roller coaster, and we are going to let gravity do all of its work, and that it's going to go down, and then it's going to do a loop de loop, and then come back through. And the roller coaster problem states that during the construction of this, they ask you how high does this need to be with respect to this. Okay? So it seems like a pretty difficult question to even start with because they two seem like two different things. But in order to do this, it's actually a little bit easier than you think. So, first of all, this height that we're talking about is going to be the 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 maximum height. It's going to be the point in which the roller coaster car, which is going to be located right here, is about ready to leave the track and plummet to its doom. So we're looking for that moment, and then obviously we'll build our roller coaster loop-de-loop a little bit lower than that in order to be safe. But in order to do that, we need to figure out what is that point there, what is that height, what is that velocity need to be in order for that cart to still stay on the track. Now, hopefully, you see that it's a uniform circular motion problem, and unlike all the other uniform circular motion problems I've talked about, we've been left with this idea that velocity is constant. This is not the case for this problem, but it turns out it's not important because we are only going to be really concerned with this point at the very top. Okay, that's the point in which we are going to be dealing with that velocity. So we are going to ignore all of it and just simply concentrate at the top. Cool. So, like a uniform circular motion problem, what we start off with is we start off with drawing our free body diagram because it is a force problem. So here's my cart. It's upside down. The two forces that are acting on it are gravity and normal force. Okay, I almost drew the normal force up, but that made no sense. So those are the two forces that are acting on the cart at that moment. Okay, but if we are talking about the situation in which the cart is about ready to leave the track, that means that there will not be a normal force, and we are only left dealing with the force of gravity. Now, we now move on to the next part of this, and we say, well, okay, I know that there's only one force, which is mg at the very top. I know that it's causing the object to move in a circular path. So I am just going to simply say that the sum of my forces is equal to mass times acceleration, which is equal to mg. And in this case, it's a circular motion problem. So I can do a substitution for A, saying m v squared over r is equal to mg. And then more importantly, the sum of my, this force part goes away, the mass part goes away, and I'm left with v squared is equal to gr. Okay? Not able to solve it. I know that gr is going to represent, or r is going to represent this, and I need 2 times that, but that's not a big deal. Okay? Well, the other thing about this problem is that I know what forces are doing work in my system. I know that gravity acting at the very top of this incline is going to accelerate my cart all the way down, and then my gravity is going to do negative work as it goes back up, and then eventually do positive work on the back down. So the idea is to be able to calculate how much original work that gravity is going to do and compare it to the amount of work or the amount of energy that's associated with the top of this incline. Okay, so with that, I'm going to move over to here because I want to leave this where it needs to be. It's where it should be. Okay, and let's start at the very top. So if it starts at the top of the ramp, I can say the amount of energy is equal to mgh. I'm going to assume, oh, let me pull that down a little bit. I'm going to assume that there's no gravitational potential there. Or, sorry, no kinetic energy there and only gravitational potential. That energy is going to be transferred to this new point right here. Now, we definitely do not want to come to a stop. We want to have a velocity. It's important that I have a velocity. Okay? So now I have my mgh, and that is going to go to 1/2 mv squared, which is this motion that it has at the top, plus this additional bit of gravity, or gravitational potential energy it has at the top. Okay, I want a little bit over there. Okay, so this is my initial potential energy. This is the potential energy at the top of the loop-de-loop. And this is the amount of kinetic energy it has at the loop-de-loop. Cool? Boy, that looks kind of ugly. Let's go ahead and do this again. So mgh is equal to, because we're not assuming any energy is lost, to 1/2 my mass times my velocity squared, which we said is equal to gr plus mg2r. Okay? Now from there, I see that the mass of the cart doesn't matter, which should make sense to you if you've ever been on a roller coaster. They don't ask you how much you weigh. They only ask you how high you are. So that'd be gh is equal to 1/2 gr plus 2gr. So that would turn into this would turn into 4/2. So I'm left with gh is equal to 1/2 gr plus 4/2 gr. So that means that gh is equal to 1/2 gr plus, which would give me not 4, 5 halves gr is equal to gh. And obviously the g's can cancel. So I have h is equal to, well, I can simplify that to 2 1/2 r. So that means that this roller coaster has to be 2.5 taller than the radius of the loop-de-loop. Cool? That is the infamous roller coaster problem. It's in two parts. One dealing with uniform circular motion. The second part dealing with energy. It is a difficult problem. I made it look easy. I managed to get it done in 8 minutes. But that's simply because I know the process. Do not expect yourself to be able to blow through this problem very quickly. Just keep that in mind. Okay?